Let's do some problems having to do with stereochemistry, but with molecules where the stereochemistry is generated completely, or at least in part, through a chemical reaction. Here's an example. So let's start with this compound. And the first question for you is, other than just a carbon chain, what is the other functional group within this molecule? Well, what you have here is a carbonyl group. And can you be more specific than that? What kind of carbonyl is it? It's a ketone. The next question for you is this molecule chiral? That is to say, is it identical or not with its mirror image? And maybe just try to answer the question kind of right off the bat, if you can. Well, one thing we're used to looking for in a molecule that's chiral is some source of chirality, and very often, maybe typically as far as organic chemistry is concerned, that has to do with a tetrahedral carbon with 4 different things attached. So really, we just have a straight chain alkyl chain here with a ketone carbonyl here. So what is the hybridization at this carbon? sp2. And the geometry that goes along with sp2 is trigonal planar. So one way of thinking about this functional group, and the way that I've represented it, is that the functional group, the carbon of the carbonyl, and the 2 things attached to it, these 2 groups, as well as the oxygen, all lie in one plane. So another way of thinking about this is that this is flat. So there really is no source of chirality in this molecule. The answer to this question is no. It's not chiral. You can convince yourself of this if you like. I won't do it here. But draw the mirror image, and then you can take that and just turn it over, and it will match atom for atom with the original. So no, that's not chiral. Okay? But I want us to imagine, and this goes back to what you know about carbonyl reactivity. So first of all, we're going to treat this ketone with a source of H-. Exactly what that source of H- is need not concern us now, although it will a little bit later in the semester. And also in the lab, I think you will do addition of hydride to carbonyls. And then as a second step, we're going to add H+. And recall, you've seen this kind of reaction before. We have to separate the 2 steps. First add H-, then add H+. If we try to put everything together, the H- will simply react with the H+, and that will be the end of the reaction. So the first thing I want you to think about in step 1 is, given what you know about the carbonyl, and given how I've oriented the carbonyl in the plane of the board, and knowing that the nucleophile H-, or I hope you know, is going to add to the carbonyl carbon as a nucleophile, from what general direction, or possibly more than one direction, from what general direction would the hydride come? Well, you may remember that the addition of a nucleophile to a carbonyl is more or less perpendicular to the plane of the carbonyl group. So one direction of approach would be for the hydride to come from here, from outside the board, or from the top, if you will. So let's say, top face addition. And what's the alternative, right? Since this is flat, here's the plane of the carbonyl. One way the hydride could come would be from this side. What's the other way? Well, the hydride could come from the back. And so, I don't know, maybe I can do that in yellow here. So what I want you to think about is, first of all, what would be the consequences of top face addition
of hydride in the first step, followed by addition of H2. And then the yellow pathway, if you will, what if the hydride adds from the back of the board and then you add the H+. So pause the video and see if you can write those two different modes of addition to the carbonyl group. The crucial things here are the carbonyl group is flat. I've happened to orient it in the plane of the board. That's convenient for me. And I also know from our previous study of carbonyl chemistry that the nucleophile should add more or less perpendicular to the trigonal plane of the carbonyl group. Okay, so first of all, let's look at the top face addition possibility. If the hydride comes from here, the new bond between this carbon, so this is my carbonyl carbon, I don't know, let me just put a little star next to it like that. The new carbon-hydrogen bond at that starred carbon, so here it is. And so this is the top face addition of the hydride. Here's the hydrogen that added as H-. So it should be on the wedge. Here's a problem-solving hint for you. In these problems, it's easiest just to keep the main carbon chain oriented right in the plane of the board, and then have the groups off of the main carbon chain be on wedges and dashes. Well, what does that mean when hydride adds to this carbonyl, right? So remember how this works. Here comes hydride, it adds to the carbonyl. This double bond becomes a single bond, and then this oxygen picks up a negative charge. And then in step 2, you protonate that negatively charged oxygen. So the OH group that's going to result is back like that, okay? So this is the product resulting from top face hydride addition. All right? What about the bottom face addition, the yellow product? If the hydride, instead of coming from the front, from where you're sitting, comes from the back of the board, what would the product look like? The main carbon chain would be the same, like this. But the hydrogen, the hydride, would have added from the back. And then after step 2, after the protonation step, that would mean that the OH group would be forward. So this is from bottom face hydride addition to the carbonyl group. So here's the question now. We examined the starting compound, and we determined it was not chiral. It didn't have any stereogenic carbons, those carbons that we call chiral centers. How about the products? Do the products have any stereogenic carbons? And are the products chiral? Well, look at this. We've generated a carbon here that has a hydrogen, an OH, a methyl, and a propyl group attached. So those are 4 different things. So yes, this is a stereogenic carbon now. And so is this one. What is the relationship between these two structures? These are enantiomers of each other. So I knew that because these structures have one and only one chiral center, and the configuration at each of those chiral centers is opposite. Okay? So these two are enantiomers. Is this molecule chiral? Sure it is, right? It has to be chiral if it has an enantiomer. So chiral, yes. And how about this one? It's also chiral. So going back to the original structure, this carbon, maybe I shouldn't have used a star, because a star I've been using a lot in terms of designating a chiral center. So this is not a chiral center at this point. But once hydride adds, you manufacture a chiral center
So sometimes this type of carbon right here, or this type of structural element, is called a pro just means before, a prochiral center. In other words, it's a center within a molecule that through the agency of some chemical reaction can be converted into a chiral center. All right? This type of concept is very important in biology because biology cares very deeply about chirality and handedness and stereochemistry. So in biochemical pathways, a lot of times you have a prochiral element like a carbonyl group, and then by addition of a nucleophile, say hydride or some hydride equivalent, you generate a stereocenter. And that needs to be done in biology in a stereo-controlled type of way. Okay, so I want to just quiz you on your terminology here. Let's imagine that we had a one-to-one mixture of these two. So one-to-one mix of these. First of all, what kind of mixture would that be? Can you think of the term? It starts with an R. So that would be a racemic mixture if we had a one-to-one mixture of these two. And then the next question is, if I did have a one-to-one mixture of these two enantiomers and I measured the optical rotation, by how many degrees would the plane of polarized light be rotated in passing through this racemic mixture? The answer is 0 degrees. So remember, in a racemic mixture, you have an equal number of molecules of each handedness. So when plane polarized light goes through that mixture, one enantiomer is going to rotate the plane by x degrees to the right, and then the other enantiomer is going to rotate the plane by x degrees to the left, and the net rotation is going to be 0. Okay, so if we have a racemic mixture, we would see no optical rotation.